Hello, everyone. I would like to thank the International Association of Agricultural Sustainability, the International Agricultural Innovative Conference, and of course, Dr. Lee for this opportunity. View this presentation as Sustainable Agriculture and Community Development under Uncertainty. Let's review what we will cover in this presentation. A description of the program under study and a very small representative description of Part 1 of Phase 1 of the findings. Regional background and demand of the sustainable ecological water quality food system, and the pressing sustainable agricultural investment and technological innovational issues. The purpose of this program under study is to better understand any barriers to the adoption and use of information communication technologies, identify factors that would assist in overcoming these barriers. ICTs, or information technologies, are inclusive of all IoT, smart systems, and systems platforms. We begin looking at a worldview that looks like this: intelligent communities, smart cities, information communication technologies, which include the Internet of Things, the IoT industry, and of course the Internet of Things for agriculture. The methodology and methods for this program under study is presented here. Institutional organizations and agency representatives are organized in this manner. The triple helix model for analyzing community and economic development is the theoretical underpinning for this program of study. These research questions were posited to more than 100 representatives, actors, place observations, and survey interviews. Top categorical themes are presented here. That is, awareness or unawareness of the use of ICTs, opportunities or basically lack of knowledge of those opportunities, collaborative behavioral skills, which were needed and are still needed, infrastructure needs. We will expand on the sub-theme of agricultural technology issues for this presentation. The potential use of information communication technologies brought about the following understanding of the regional area: water quality issues and farming practices. Governing behaviors directly emerged: daily decisions under uncertainty, the bounded rationale model of constraints, transformative and sustainable agricultural practices within the bounded rationality of community development. Here's our region and our location. This is our Great Lakes region that we fit within. Right down here is Lake Erie. So there are 48 million population, approximately 10% of the U.S. and 25% Canadian. Source drinking water for more than 48 million population. 21% of the world's supply of surface fresh water. Watersheds that are drained into the Great Lakes are affected by agriculture and city and town drainage, these particular watersheds. We're all regulated by the United States Code and the Clean Water Act. The United Nations global leadership informs us water quality, energy, ecological resources are critical to the world's future. Here we focus on our study sample. So we have a population in this particular region of 162,583 citizens. We have 4,336 farms and an average farm acre size of 229 acres. What is happening? Extreme weather events, extreme rainfall events such as 1 to 3 inches of rainfall in less than 3 hours. Washed off nutrients such as phosphorus, potassium, and other fertilizers, often initial seeding, we see unplanned ponding areas from field runoff, where runoff from algae growth grows within a few weeks. Sediment and nutrient loss without filtering quickly moves downstream. This photo is about 3 hours after 1 or 2 inches of rainfall. You can see the remains of algae growth in the future. In the future, edge of field monitoring may help establish better practices. This is the same ditch further downstream. Ditches clear 80% of the water through the watershed within 3 hours of extreme rainfall. 50 years ago, prior to previous agricultural development, the watershed's filtered rainfall had an estimate of 2 weeks flowing downstream. Farmers must remove the water from these fields through tiles and ditching to keep a yield. Monitoring tools on events or for analysis and intervention are not common for most producers. Now on the way to the Great Lake, Lake Erie, in less than 4 hours from the extreme weather event. More than 1 to 3 inches within a very short period of time, maybe an hour. Here's another view. The trip looks like this. Here's our region, and down through these tributaries into the river and out into the Great Lake. By midsummer, the lake looks like this, with water quality problems that follow. These goals have been set addressing the situation. Here's the watershed. There is much activity in analysis for phosphorus, potassium, and other nutrients. Manure through hand sampling in this particular area. Lake Erie goals, 40% reduction in total phosphorus, 40% reduction in soluble reactive phosphorus. By late summer, several of the shores of the Lake Erie often look like this. Of course, if drainage tile cannot remove enough of the extreme weather rainfall event, damage is done. An estimated 2 days delay in standing water for this picture. This field damage may be less than 2 days, often several extreme rainfalls in a very short period of time over a few weeks. Surviving yield will result in patterns similar to this. The United States Department of Agriculture and the Environmental Protection Agency has stated these goals for this region. The goal for agriculture by 2050, increasing production 40% by 2050, reducing environmental footprint 50% by 2050, water quality nutrient loss 30% by 2050, food loss and waste 50% by 2050, carbon sequestration, greenhouse gas net reduction, and of course renewable energy 15% and 30% by 2050. The top photo is runoff in a natural ponding area close to the river, and this yield is in photo. This photo is below, which is adjacent to the ponding area. The photos were taken in the same day at the same period on the same acreage. Today's yields must be looked at in light of the projected goals for 2030 and 2050, along with the need for new investment, innovative technologies for future agricultural production. These photos were taken recently. There is pressing demand to design for the future. World population growth, 7.9 billion to 9.7 billion. Food demand will rise more than 25%. Mitigation of demands for global ecosystems to meet food and food security. Agricultural demands for better management of land, energy, fresh water, further resources required for the future. A sustainable ecological system approach with a viable natural environment, sufficient economy, nurturing community in light of the earlier topical findings of the deficiency of awareness, of opportunity versus problems, of collaboration skills versus short-sightedness and decision-making, infrastructure, technology needs. We must begin engaging the needed resource support for organizations similar to this one. Key, however, is education and demonstration of best practices, allowing for observability, compatibility, triability, and relative advantage dealing with complexity for adoption and adaptation of new practices. We found so far that regionally understanding, such as smart intelligent platform stacks, awareness is absent from a regional consensus of representative leadership. Similarly, sustainable understanding is also absent. Specifically analyzing sustainability, mapping different meetings, and technology usability. In conclusion, information communication technologies, ICTs, will continue to grow with systems of systems. Opportunities for innovation and investments within a food system industry are strong. Patterns of uncertainty in information communication technologies, ICTs, will continue to become the next best thing for investment with innovation technology opportunities. Future research opportunities will increase for testing sustainable smart technological systems. This is a great time to be in agriculture technology and applications of innovative ideas. Education and information availability is key. Aggregating information analytics presents opportunities. Methods for critical and scientific research must be applied. Socially communicates consensus, acceptable common practices. Super collaborative social behavior enables success. Investments in infrastructure and advocates for government practices must be put forth. There's an opportunity to meet the needs of agricultural, technology, and ecological demand, investment, innovation, and change, meeting global demands for sustainable water quality and the United Nations goals. Thank you for listening.